Okay. Hi friends. Today I will give you a brief idea about the register organization of 8086. Okay, let us see what are the various registers present in 8086. Okay, I already mentioned the 8086 mainly contains 14 16-bit registers. Let us see here. So 8086 mainly contains 14 registers. See here, AX, BX, EX, DX called as general purpose registers of size of count 4 segment registers. Yes, first letter S indicates segment registers. I will give you functioning of each one in detail. 4 registers and one flag register and 3 pointer registers SP, BP, IP and 2 index registers SI and DA. Put together 5, 6, 10, 14. Total 14 registers are there. Let us see the functioning of general purpose registers. So general purpose registers are also of size 16-bit, but these registers can be used either 8-bit or 16-bit. Let us see for 16-bit operation directly we can use AX, BX, EX, DX. X for extension nothing but 16-bit. For example, I need 8-bit register only. Then we can use AL, AH. Generally, A is accumulator register. AX is accumulator register, 16-bit register. B is a base register. C is a count register, and D is a data register. So now this accumulator register can be split into two 8-bit, AL and AH. AL name is accumulator lower byte register. AH is accumulator higher byte. Similarly, base lower byte, base higher byte. Count lower byte, count higher byte. Similarly, data lower byte and data higher byte. So byte means 8 bits, 0 to 7. Higher byte means 8 to 15. Like that, these 4 registers can be split into two 8-bit registers. Whereas the remaining registers used only for 16-bit. Even for 4-bit or 8-bit operation also, we can use complete 16-bit. No division like general purpose. It is possible only in general purpose registers. Now let us see the functioning of each register detailedly. So coming to register, see here. Let us see the registers of 8086. In that, let us see general purpose registers only. First of all, AX. I already mentioned it's an accumulator register. So if it is AX for 16-bit, so this AX can be split into two parts, 8-bit to 8-bit. So name it as AL. Similarly, AH. AL is accumulator lower and AH is accumulator higher. So let us see a few points for AX. So one is it's a 16-bit register. Second, it can be divided into two 8-bit registers, namely accumulator lower and accumulator higher. So one important feature of this AX register is it is also called as a default register. So for all arithmetic and logical operations, your AX register act like a default register. So what is default register? For example, I am writing like this: add AL, comma BL. So here the data that is present in BL is now add with AL. Result is stored in actually AL, but the size of AL is 8-bit only. But if add two 8-bit numbers, your result is more than 8-bit. Where that remaining 8-bit result is stored, it is stored defaultly in another accumulator register called as AH. So AH will take the carry result in this particular example. That's why the register AX is also called as a default register. So among all 14 registers, only accumulator register is also called as default register. Okay, right. So not only arithmetic, for all arithmetic logical, mostly the accumulator register can be used as a default register. Right. So next one is BX register. BX register also split into two parts, BL or BH. So BL for lower 8-bit and BH is higher 8-bit. So BX is called as a base register. So it is also divided into two 8-bit registers, BL and BH. Okay, so BX register is used like a normal general purpose register. Right. So for all general operations, maybe data transfer operations or any logical operations, we need registers, means we can use either BL or BH for 8-bit, or for 16-bit we can use BX register. Do next one, CX register. CX register also call it as a count register. It is also divided into two 8-bit registers, namely CL and CH. So name itself, it's a count register. For example, I need to add 8 numbers. So instead of writing 8 additions, we can simply call it as a count register with value 08. Then we can write add and writing like a loop. Then it will perform 8 times addition until this count completely clears to 0. For example, see here move CL comma 08H. So initially I am quoting as CL with 08H data. So now I am writing like a decrement CL or something. Then the CL is decrementing and it will continue addition of 8 numbers, for example. Okay, for every addition the CL is decrementing. For example, first addition, okay, if I am writing, then CL is decrementing. Again continuing loop. Okay, if I want, I will write like a code. So for example, one loop writing like a one label first L1. See here I already mentioned this value. So for example, add AL comma BL, then loop L1. If I am writing like this, AL data is add with BL data. After adding, then because of this loop instruction, CL is decrementing by 1. So after addition, CL becomes 07. Again, it is not completely because loop instruction checking two things. Is it CL is 00 or not? So GL is not 00. So then again it will go here. Again my BL data is add with AL data. Result is stored in AL. Okay. Again my because of loop instruction, again my CL is decrementing. So 07 becomes 06. Okay, is it 00? No. Again it will go to L1. Like that, this loop repeats how many times? 8 times. In those operations, we are using count register, preferably CX register. So this is for loop operation. In general, also we can use this CX register like a general purpose register. Similarly, the next one is DX register. So it is also divided into two parts, DL and DH. DL is data register lower byte and data register higher byte. So this DX register also used as another default register for 16-bit operation. So already in this example, we are observing whenever AL is add with BL, result is stored in AL. If carry result is there, it will store in AH automatically for 8-bit. For 16-bit, what happens? For example, if I am writing like this, add something like AX comma BX. In this case, what happens? 16-bit BX data is now added to 16-bit AX data, and result is stored in AX. But if you add two 16-bit numbers, result is more than 16-bit. The remaining result is stored in this DX register. Even we are not initializing here, DX register will take the other part of the result. Means after 16-bit, if any carry appears, that result will be stored in DX. But it is possible only after initializing DX. So you should initialize DX, then only DX will take the remaining part of the result. So it is a second default register is DX. First default register is AX for 8-bit operation. This is for 16-bit operation. But here you should initialize DX, then only it will take the remaining part of the results. Okay. So these four related to general purpose registers. Coming to next one, segment registers. So let us see once segment registers. Here how many segments or registers are present? So I already mentioned there are 4 segment registers named as code segment register, data segment register, extra segment register, and stack segment register. Let us see what is the need of these 4 segment registers. Observed here in this particular diagram. So I already mentioned 8086 having 20 address lines. Because of 20 address lines, 2 power 20 memory location it can access. 2 power 20 means 1 megabyte. So 2 power 10 is 1 kilobyte, 2 power 20 is 1 megabyte. So 8086 is ready to access 1 megabyte of memory. 1 megabyte means 2 power 20. 2 power 20 means what is starting address? 20 bits. So equivalent XI is 450H. 20 ones. What is equivalent XI? 5Fs. So starting address is 50H, ending address is 5FH because of 20-bit address. So this total 1 megabyte of memory of accessing capacity of 8086 can access at a time 4 segment memories only. So this total 1 megabyte of memory is divided in the form of segments. So code segment, data segment, stack segment, and extra segment, like that they are dividing like a segments only. And 8086 can access at a time 4 segment memories only, and size of each segment register is 64 kilobytes. So 64 plus 64 plus 64 plus 64, total 256 kilobytes of memory only processor can access at a time because of 4 segment register. Now the function of each segment register is each segment register can hold the upper 16-bit starting address of corresponding segment memory. For example, this is a code segment memory. So this CS register can hold the upper 16-bit starting address of this memory. For example, this memory starts at 50H, end at, for example, 4FH. Then the CS register will hold the starting address of upper 16-bit. What is the upper 16-bit here? 40H. So it will hold 40H. For example, the data segment memory starts at 10000H and end at, for example, 1FFH. Then data segment register hold the starting address of upper 16-bit. Upper 16-bit address of this data segment starting is 10000. In that upper 16-bit address is 1000H. So it will hold 000H memory here. Like that, every segment register can hold the upper 16-bit address of the corresponding segment memory. And the bus interfacing unit will initialize lower 4 bits to 0. Then we get 20-bit base address. So in order to get 20-bit base address of your segment memory, so your bus interfacing unit will assign 4 more zeros in the lower bit. We get 20-bit physical address. Okay, this is the simple role of segment register. Again telling you, segment register role is simply hold the upper 16-bit starting address of the corresponding segment memories. How many segment memories we have? Code segment. Because of code segment register, we have code segment memory. Size is 64 kilobyte. Data segment memory, stack segment memory, and extra segment memory. So these 4 are called as segment registers. Let us see flag register. We'll discuss later. Okay, now let us see pointer register, stack pointer, base pointer, and instruction pointer. 3 pointer registers are the stack pointer, base pointer, and instruction pointer. Generally, instruction point register is associated with code segment register for generating 20-bit physical address. Similarly, stack pointer register is associated to stack segment register for generating 20-bit physical address. Similarly, base pointer register is associated to data segment register or extra segment register for generating 20-bit physical address. So SP, BP, and IP are associated to CS, SS, DS, and ES for generating 20-bit physical address. So IP is associated to CS, SP is associated to SS, and this BP is associated to either DS or ES, because data segment and extra data segment, both are data segments only. These two associated to BP for generating 20-bit physical address. Okay, no other functioning. These 3 only for generating 20-bit physical address in association with segment registers. Similarly, SI and DA. So name of SI is source index register and DA is destination index registers. These 2 registers are also used like a 16-bit general purpose registers. So for example, I need to read data from external memory, or I need to send data to external memory. So in those cases, we use SI and DA. These 2 registers are also used like a general purpose registers. Sometimes these 2 registers are also used for separate addressing modes like base index addressing mode, index addressing mode, register relative addressing mode. In those addressing modes also we can use these 2 registers. Coming to our last register, flag register. Let us see what is flag register. If you observe flag register organization, so 8086 flag register size is 16-bit. So every time the representation must be D0 to D15. This is D0 bit and this is D15 bit. So for every digital representation, instead of starts from 1, starts from 0 to 15, D0 to D15. Let us see what is carry flag. Carry flag is, it's very simple. For every flag, consider carefully. Carry flag is set to 1 when there is a carry comes out of MSB bit. Means, for example, if it is 8-bit operation, whenever carry comes out of MSB bit, means it is act like a 9th bit. Okay, it starts from 0, it's act like a 8th bit. Generally, MSB bit means here, for example, 15th bit is MSB for 16-bit operation. For 8-bit operation, 7th bit is MSB. So whenever carry is occurred in the result, when carry is occurred, whenever if you perform arithmetic or logical operations, when carry flag is occurred, whenever if result contains 8-bit, and if carry comes, carry act like a 9th bit. Means 0 to 7, then 8th bit is act like a carry. If it is 16-bit operation, if result contains 16 bits, okay, then it indicates that carry comes out of MSB bit. Actually, MSB is 15 only, but result contains 16 bits total. Then we can say that the carry is occurred, then carry flag is set to 1. So finally, carry flag is set to 1 when carry is moved out of MSB bit. Okay. Coming to priority flag, U is unreserved. So it's unreserved. So it is used for future extension. So one is not used, it's unreserved. PF is a priority flag. So priority flag means it's set to 1 when result contains even number of ones. When the complete result after performing arithmetical logical operation, we get result. In that result, if result contains even number of ones, then parity flag is 1. Then third is also reserved for future extension. AF is auxiliary carry flag. Auxiliary carry flag is set to 1 when carry is moved from D3 to D4. So whenever carry is moved from D3 to D4. So for example, one number, if we consider one 8-bit number, other 8-bit number. So in that 8-bit we have D0 to D7. Similarly, another 8-bit also D0 to D7. So whenever D3 bit of first number is added to D3 bit of next number, in that particular addition, if any carry come from D3 to D4, in that case only auxiliary carry flag is set to 1. Then zero flag. So zero flag is set to 1 when result contains when result is completely 0. Zero flag is set to 1 when result contains complete 0. For example, exclusive OR operation of AL with A. So when AL is exclusive OR with the same AL, then AL becomes cleared. So result is now all zeros. In that case, zero flag is set to 1. Okay. Then sign flag. Sign flag is set to 1 when in the result of MSB contains 1. When result of MSB contains 1, it indicates your result is negative. Then sign flag is set to 1. So when sign flag is set to 1, sign flag is set to 1 when MSB bit of result contains 1. Okay, and it indicates one indicates the overall result is negative result. Okay, then other is the trap flag, interrupt flag, and direction flag and overflow. These four are very important. Consider trap flag. So whenever trap flag is set to 1, then processor will enter into single step mode. So in single step mode, instead of executing the all instructions at a time, processor will execute only one instruction at a time and verify the results. If everything is okay, then it will execute next instruction. So whenever trap flag is set to 1, processor will enter into single step mode. So in that mode, it will execute only one instruction at a time. Now next one is interrupt flag. Interrupt flag is set to 1. In that case only, whenever interrupt flag is 0, it indicates processor won't recognize external interrupts. Then direction flag. So direction flag indicates the flow of execution. So whenever direction flag is 0, then processor will execute starts from lower address to higher address. Whenever direction flag is set to 1, processor will execute first higher address, then lower address, reverse. Then overflow flag. This is very important. Overflow flag is set to 1 when result is out of range. What is out of range? How can you decide? So it indicates like this. Overflow flag is set to 1 when a carry move from carry into MSB bit and no carry out of MSB bit. In that case also 1. Overflow flag is also 1 when no carry into MSB bit but carry out of MSB bit. So if first statement or next statement, if any one is true, overflow flag is 1. So when overflow flag is 1, carry into MSB and no carry out of MSB. In that case, overflow flag is 1. Or no carry into MSB and carry out of MSB. In that case also, overflow flag is 1. Okay, rest overflow flag is 0. This is about the register organization of 8086.